Okay. So from last time, we were talking about possibly doing these double integrals over rectangles, and we defined this region R as the interval from A to B and the interval from C to D, which also corresponded to another way of writing this was all of points in R2 such that X is in between A and B and Y is in between C and D. So this just makes a rectangle. And I wanted to kind of start stressing, like we started talking about on Friday, where I want you to stop thinking of integrals as the area underneath the curve, but rather the sum, right? It's adding up quantities that are extremely small, and it adds up an infinite number of them until you get a value. So we started to draw this picture where, let's kind of use straight lines for this, where we had R in the XY plane here. Something like that. And then we had a surface. So it's always a straight line. There we go. So we have some surface here maybe. Kind of looks maybe something like this. And now we'll do straight lines. And kind of maybe right above this R is this surface that we've kind of drawn here. This is f of x and y is equal to z. And we're going from A to B. And we're also going from C to D. So the idea here is, how can we start setting up an integral that might compute the volume of such an object, right? The volume of the object that goes from the XY plane up to our surface here. So to approximate, and we're going to do this all the time. We're going to start with an approximation and then just going to keep letting it get better and better. So we're going to approximate the volume let's divide R into sub-rectangles. So what do I mean by that? What I'm going to do is I'm going to let A be this first point in X, and then I'm going to keep having a bunch of points in X until I get, and I make M of them. And this will be equal to B. So basically, I'm just subdividing our X into a lot of subdivisions. I'm going to do the same thing with Y, and they don't necessarily need to be the same number of subdivisions, but I will create some amount of them. Oh, I'm writing X. Be a Y. YI. And I create, this time I'll create N of Y. This is equal to D. So now we're subdividing in the Y direction. So looking from above, and using 5 subdivisions in each direction, what we can do is kind of sketch out what this looks like if we're looking down at our surface. So here we're in the XY plane, and our rectangle might look something like this. So this is our block R, and we're going from A to B, as well as from C to D. But now we're subdividing in each direction. We're making 5 subintervals. So let's see if we can do a nice little graphical job of this. Maybe something like not quite even, huh? They don't necessarily need to be even, but be something like that. Okay, so now I've subdivided each direction, x and y, in 5 subintervals. So I got 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Obviously, there's 25 of these little sub rectangles. But what we'll do is we'll call this R11 right in here. And this will be our R55. And if these are all the same dimensions, we can say that this is delta y. And here we have delta x. And we can kind of say that any one rectangle we can call Rij is the rectangle that goes from xi minus 1 to xi and yj minus 1 to yj. All right, so now we have these kind of labels for each of these individual rectangles, and it's arbitrary that we pick 5 here, right? It's just kind of, it looks a little nice, right? But of course, the idea is we're going to keep subdividing until these squares get smaller and smaller and smaller. But let's kind of figure out what to do with each of these rectangles. So if we choose a sample point which is xi star yj star in each rectangle Rij, we could use the function value at that sample point to approximate the volume in each Rij. So going back up to our plot here, maybe I choose for all of the rectangles, I choose the very center of the rectangle. So half of x and half of y. And then I plug this point into my function f, and that gives me the height of the surface at this location. I can use that for the height of the whole rectangle, so we can kind of draw what this might look like. So here, we're just looking at some arbitrary rectangle as the base. We have delta xi and delta yj. And the height here will be determined by f of ij star and xi star and yj star. So we plugged in our sample point, and that gave us the height of this rectangle. So instead of the surface here, we just make a rectangle with height that's given by f with our sample point. And we can also say that this delta xi and delta yj will equal this delta area ij. So we have some change in area here. It's like base. And what we can do is, if all of these cubes are placed on our rectangular grid here in the xy plane with different heights that are based off of our sample points, if we add up all of these rectangles, or now these cubes, we can approximate the volume. Now, if you use more and more subdivisions in x and y, of course, you're going to get a better approximation, right? Because maybe our curve or our surface is kind of too curvy, but as we zoom in and closer and closer and closer, they should all resemble a flat surface. And we'll just add up all of those values there. So by adding all the columns these being the columns, we can also just say cubes. We approximate the volume. So we say that the volume is approximately the sum from I equals 1 to m and the sum from j equals 1 to n of f of xij star, or we can just say xi we'll do, and then yij star, and then the area of each of those little rectangles. So we're just adding up all of the height times the area of these cubes. Now, if we keep letting the change in x and change to y go to 0, making them smaller and smaller, meaning there's more subdivisions, we better approximate the volume. Thus, the volume can be defined as the limit as both the changes of x and y go to 0 of our sum Now, of course, m and n change as this goes down. This becomes the double integral over the region R, the rectangle, of the function f of x, y, dA. If the limit exists. So this is our double integral. A function f is called integratable if this limit exists. So we talked about on Friday that we said that f was going to be non-negative, meaning that no matter what x and y we plug in, that's inside of our rectangle, we never get a negative number for f. That means that we can create this volume because we don't have any of these negative volume components, right? And that would just be bizarre, right? But one question is, okay, here's this double integral and it has this subscript r here. How do we evaluate anything like this? How do we even get started? So much like differentiation, we're going to do integration across x, y, and so on. And all the while, if we're integrating with respect to x, we're going to leave the y's as constants and vice versa. Right? So this is just like partial differentiation. You can kind of think of it as like partial integration, right? Where you're taking the integral with respect to a certain variable and all of the other ones are maintained as a constant during that process. So first, I want you to consider some function that we'll call a that is just a function of x and is equal to the integral from c to d of our function f of x and y dy. So you can imagine here that we're doing something like this partial integration. So if I integrate this function that has y's in it, then what happens is this is a definite integral. So I have bounds, I have c to d. So you can imagine that I integrate out all of the y's that are in this function. Right? So once I'm done with this integral, there is only a function of x that remains. Okay, so now what happens if I have the integral from a to b of this function a with respect to x? Okay, so this is a function of x. I certainly can integrate it with respect to x. Well, let me go ahead and replace a with our definition here. This is the integral from c to d of our function x of x and y dy. And then once I'm done integrating that with respect to y, I integrate it with respect to x, because the thing that comes out of this integral in the brackets is just a function of x, right? So it's perfectly fine for me to just integrate with respect to x here. And then at the end of the day, I should just get a number. Well, one way to write this is to just drop these brackets. So I have a to b, the integral from c to d of the function f of x and y dy dx. So here we can read off which one is being integrated first, right? The innermost one is I'm integrating with respect to y first, and then the outer one says that I'm integrating with respect to x after that. So if we start to think of these as sums, what's really going on here? Well, for that, why don't we go ahead and look at our rectangular grid to kind of get an idea of what's going on. So remember, these integrals are sums. So remember that we're doing dy dx. So we're doing y first and then x, and we have our bounds. So let's scroll back up here to our rectangle and our subdivisions. So in the discrete way of doing this, we did y first. So that means we add up for any fixed value of x, we add up all of the rectangles in the y direction. So we add all of these up. We add up all of the volumes in this direction. Then the sum is over x, right? So I move over, and as soon as I'm done calculating all these y's, I have to add up another sum in this direction. So I keep moving across and adding up all of these like that. But notice that I'm going in this direction. So I start at x equals a, I add up all the y's, I move a little bit, and then I add up all the y's again, and then I add up all the y's again, and I add up all the y's again. There's a reason I called it a of x. So you can think of a of x as the area along each trace. So maybe along each of these traces, I have the function that maybe looks something like this, right? And I add up I have for any fixed value of x, I now have just this trace that has an area. And then I add up all of those areas and I accumulate a volume. So that's kind of the machinery of what's going on here. So A of x represents for any fixed x the area of that trace. And then I add up all of those areas of all of those traces from A to B in the x direction, and I generate this volume. Okay. So now let's talk about a theorem, which is Fubini's theorem. If f is continuous, on the rectangle that's defined from A to B in the x direction and C to D in the y direction, then the double integral over the rectangle of our function can be written as the integral from A to B, the integral from C to D of f of x, y, dy, dx. Now you might be asking yourselves, well, why was it so necessary for us to go the y direction first, add up all of those areas along that trace, and then go in the x direction? Well, there's not. In fact, because this is a rectangle, it's really nice for us to actually reverse this order. So we can actually write in the opposite order as well. We can go from C to D, and then the integral from A to B of f of x and y, dx, dy. So this is the innermost integral, is the area of the trace for any particular y value. And then we go in the y direction, we add up all of those areas and create this volume. Now we can only do this really cleanly because this is a rectangle. We'll kind of get into what happens when we're looking at arbitrary domains, but for now we're sticking to a rectangle. So continuing, if f of x and y is equal to some function of x times some function of y, then the double integral over the region R of g of x and h of y dA, this is equal to the integral from A to B of g of x dx times the integral from C to D of h of y dy. And it's just the product of these two integrals. The reason for this is because, remember, if we're doing this partial integration, and we had some integral, say A to B, C to D, of g of x and h of y, we're doing dy dx. Well, if I do this y integral first, this thing here this is a constant. So why can't I just move it on the outside of this integral? So I can have a to b g times the integral from c to d of h of y dy dx. So this thing here will just give me some constant, right? This whole integral here is equal to a constant. And it's certainly a constant with respect to x. So why don't I move this whole thing outside? And then I get the product of these two integrals. Okay, so let's go over just two properties, and then we'll talk about general regions. So properties. If I have this double integral over R, and I have functions f plus g, integration is a linear operator. And that comes with some really nice properties. Ooh. Should be plus, there we go. So we can distribute this operator across these functions, so long as f and g are integratable. If I have some double integral of some constant times a function, then of course I can move out that constant. It's another property of being a linear operator. You talk about linear operators more in depth in DiffyQ. In fact, that they have these types of properties. Okay, so obviously we're not going to be taking these double integrals over rectangles indefinitely. Imagine that we had some kind of general region. How do we kind of cope with that? How do we do these double integrals then? Oh, you know what? Before we dive into that, why don't we actually do an example of a double integral for a rectangle? Getting ahead of ourselves. Let's do an example of, so we're going to calculate this double integral when I have that f of x and y is equal to 1 minus 6 x squared times y, and R is the rectangle 0 to 2 and negative 1 to 1. So Fubini's theorem says that if this is the case, that our double integral over R of our function f of x and y dA, I can write this as, we can either choose to do x or y first. So I'm going to write my double integrals here. I have my integrand, 1 minus 6 x squared times y. I'm going to do the orientation dx dy. This is arbitrary. We could have done either way. But I have to make sure that my bounds are correct. So in the x direction, I'm going from 0 to 2. And later I'm doing the y, which is negative 1 to 1. So let's go ahead and integrate this. So this is -1 to 1, and then I'm going to do the x integral first. So I integrate with respect to x, where every y is considered a constant. So this term here gives me an x minus, and then I increase the power of this here by 1, and then divide by its new exponent. So I get 2x cubed times y, and this gets evaluated from 0. Actually, I'm going to write it like this just so we can keep track that it's x that's being evaluated. X equals 0 to x equals 2. And then we have dy. So this is still the integral from -1 to 1, but I'm going to go ahead and plug in our bounds here. So we go ahead and plug in 2. We get 2 minus 16y, and then we subtract when we plug in 0, but that ends up just giving us 0. So this is all that remains, dy. Well, we can do this. This is just the integral, or sorry, once we integrate, we get 2y minus 8y squared. And we're evaluating this when y is equal to -1 and y is equal to 1. So we plug those in, and we get 4. So that's basically how we're going to be doing this integration. We have to figure out which we're doing is x and y first. In this case, it's either, because we're doing a rectangle, but we'll see for general regions that this is not the case. And then we just do systematic integration across, right? So I did my x integral first, where y is considered a constant. I plugged in my bounds. Once I did my integral, then I went ahead and now I just have a function of one variable left to do with a dy. I go ahead and do that integral, and then I plug in my bounds. Okay. So now for general regions. Actually, why don't we take our 5-minute break here? That's actually a pretty good time. So let's go ahead, get some water, use the restroom, and then we can come back in about 5 minutes. Okay, so let's keep going. Let's start talking about these double integrals. Over general regions. So consider some region we call D that is not a rectangle. Let's do some drawings here. So maybe go the other way. There we go. So maybe we'll have some different regions here. Maybe here I have x goes from A to B, but I have a function that describes this bottom section here that we can call y is equal to maybe g1 of x, and up above it's bounded by a function g2 of x. Maybe we have something where we go from a to b in x, where we have some function that comes up, barely touches right here, and then comes back down. What we would have to do is split this function up. We would say that y is equal to maybe a function g1 of x, and then we have y2 is a function g2 of x. So not much has changed actually from this guy here. This is still region D. But maybe we could also have this same shape, but maybe it's rotated. So it barely touches some value D. And then we have y is equal to c here. This time we can say that the left is x is equal to maybe a function of y, called h1. And over here we say h is maybe a function of h2 of y. So pretty much we're going to have these split functions that kind of define these arrows that I'm going to be drawing. So we're going to be doing, again, these x or y first. And this is where we're going to kind of start drawing these arrows across. And we'll kind of see that as we go forward. When we look at certain regions, what's the best way, or what might be the only way that we can integrate over these guys. So let's go over type 1. If f is continuous, on some region D, such that the region D can be written as the set of all x and y that exist in R2, such that A is a lower bound for x, and then we have an upper bound for x that's B, but we have that y is bounded by two functions, g1 of x and g2 of x. If we can write the domain in such a way, then our double integral over the region D of the function f of x and y dA can be written as the integral from a to b of the integral of g1 of x to g2 of x, f of x y dy dx. And it has to be in that particular order. Because let's kind of look through the logic of this. If I look at these inner integral right here, I'm integrating with respect to y, so all x's are constants. But when I plug in these bounds, these are functions of x. So I get rid of all of the y's and I plug in functions of x. This was already a function of x, so then the only things left are x's. And then that's why the x integral goes on the outside. If you think about the reverse order of this, it doesn't work. If you do x first, then you get rid of all the x's, then you do the y's, but then you substitute in functions of x's. Doesn't work that way. So geometrically, what's happening here? Well, if we kind of look up at above, maybe it looks something like this. This is a type 1 type of situation. So let's kind of sketch that down here and see what might be going on. All right, let's think about this as sums again. So maybe I've got little n pieces here, A and B, and I have an upper function and maybe a lower function here. So this is y is equal to g2 of x, and then y is equal to g1 of x. So going back and kind of talking about these sums, what's going on here? So y, this first integral, the innermost integral, is summing up the traces for at any fixed x, right? So I have some fixed x, and I add up the trace in that direction, starting from this point to this point. So it goes from here to here, right? So any fixed x gives me the trace, the area of the trace in this corresponding direction. Then when I do the x integral, the outermost one, I'm adding up all of those areas. So I add up all of those traces and I create this volume. But notice if you try to do it the other way, right, it doesn't work. I can't go from this direction because I have all of these weird bumps, right? I can't start from some arbitrary fixed y direction and go from A to B, because now look, I'm including all of the stuff that doesn't matter, right? if I'm trying to go from A to B and then add up those traces, I have these regions that just don't make sense. So that's why we have to do this particular order. I have to go from y first because there's functions that define this upper and lower. So now let's look at a type 2. If I have that the region can instead be defined as x, y, so all the points x, y that are in R2, such that y is bounded by these constants c and d, but x is bounded between functions h1 of y and h2 of y. Then my double integral over the region D of f of x and y dA is the integral from C to D, the integral of h1 of y, h2 of y, f of x and y, dx dy. So notice that we reversed the integration order, right? Before we were doing dy dx, but now we're doing dx dy. So again, let's kind of look at this and break down why it has to be this way. If I look at this innermost integral, I'm integrating with respect to x, so I get rid of all of those x's and I replace them with functions of y. Then the integrand is just a function of y, and I can integrate with respect to y and get a constant. Perfect. If I do it the other way, it doesn't work, right? If I try to do y first, I would get rid of all of the y's and substitute them with constants. So then I would have a function of x. I would integrate with respect to x, but then I would have to plug in functions of y. right? Then this whole right-hand side would just be a function of y rather than a constant, which it certainly shouldn't be. So the logic there doesn't work if I kind of reverse the order, but now let's do a sketch. So same thing. So a type 2 might look like a rotation of what we've just done from up above. So maybe we've got some straight lines here, and then I've got a left function and a right function. So here, this is from C to D. And then my left might be some x is equal to some h1 of y. And then this is x is equal to some h2 of y. So what's happening here is I'm doing the x direction first. So I'm going across in the x direction, and I start at h1 and I end at h2 for any fixed y. So I'm creating these traces and I'm collecting the area of those traces, right, for any fixed y. Then, other direction, I add up all of the traces in the y direction from C to D. So I take all of these traces and I add them up, right? So that's how we kind of compose this volume. Again, it doesn't work if I reverse this order, because what happens is I'm going from C to D for any fixed x. It doesn't work because, again, I have these regions where I'm looking at the trace when the trace doesn't exist in the region D. So that's why we have to do in this particular order. Okay. So most likely it's not going to be given to you if this is a type 1 or a type 2 type of domain. It's not going to be, oh, this is type 1, please integrate this, or this is type 2, please integrate this. It's going to be up to us to figure out is, how do I integrate this thing, right? So the best advice that I can give you is sketch. Moving forward, get practice, sketch it, right? It doesn't matter if it's a bad sketch, but we got to start thinking about what's happening here. We have to start sketching because it's going to get worse. So we really have to get these basics down. So let's look at an example. And I think this is a pretty important example. We're going to calculate this double integral over this region R of the sine of x over x dA. When R is the triangle in the xy plane bounded by the x-axis y is equal to x and x is equal to 1. Okay, first thing, we're going to sketch this. We're going to sketch out this region R. What does this look like? I don't even care what my integrand is right now. I want to know what the region R looks like. So I'm going to go ahead. We have our y and x plane here. And then I have the x-axis, so I have my x-axis here. And then I have the line, y is equal to x. We have some 45-degree angle, like that. And then we have the line, y equals 1. So maybe somewhere out here. So our y is equal to 1. Okay, and this is our region R. This is the region that we're integrating over. So we have to figure out, is this a type 1 or is this a type 2? So why don't we do this? Why don't you all look at this region and you can private message me or do everyone. What are your guesses? Is this a type 1 or is this a type 2? Like, come on, let's see those answers roll in. What's going on here? Okay. I'm seeing some answers. All right, I'm liking it. I'm liking it. So I see a lot of type 1s. I see a lot of type 2s. Then there's some answers here. It's both. This is both a type 1 and a type 2. Okay, so let's take a step away from the problem for a second. Let's don't care about the integrand. Why is this both? So imagine that I wanted to do, I wanted to look at the traces for any fixed x, right? So that means I'm integrating with respect to x first, or sorry, I'm integrating with respect to y first for any fixed x, right? So I'm adding up all of these traces, and I start from the bottom of the triangle up to the top, right? So this is perfectly fine. And then I can go in this direction and add up all those traces. Perfect. This is exactly what we said was a type 1, right? We're drawing these vertical lines, and then we add up all the traces starting at x equals a over to x equals b. So this is perfectly fine. I've included everything in my region. Okay. What about the other way? Well, I can start over here and go out this way and make these traces. Right? I can go out from the left over to the right. And then I go from y equals 0 all the way up to the top of this triangle, and I add up all of those traces. So this is in fact a region that's both. So it doesn't matter which x or y we go, which ordering we do, we just have to be consistent with what we choose as our bounds, right? A lot of mistakes that I see when it comes to integration is if the region is not a rectangle, you should never have your bounds being all constants. If they're all constants, that means you're doing a rectangle. So let's choose a particular direction and see if we can do this integral. So let's treat it like type 1. So if I do it like type 1, I can write out my region R as the set of all points in R2 such that now x is bounded between 0 and 1, right? So actually, let me get rid of all these lines here. Because this is the way what we're going. So our traces, the range of our traces is the outermost integration bound, right? And that means that x goes from 0 to x equals 1. So that means that we say 0 and 1. And then the actual trace itself goes from y is equal to 0. So we have down here y is equal to 0. And then it's bounded above by this function of x, which is in fact just x. So y goes from 0 to x. Okay, so that's one way of writing our region as a type 1 type. So now let's look at this integral. I have the double integral over r of sine of x over x dA. So we can write this as the integral from 0 to 1, and then the integral from 0 to x. We have our integrand, sine of x over x dy dx. So that's how we set up for a type 1 type of integral here, right? So let's go ahead and see if we can integrate this. So we go from 0 to 1, and then we integrate with respect to y. Well, there aren't any y's, so this is just a constant with respect to y. So it's pretty easy for an integral. It's just y times the constant, sine of x over x, evaluated when y is equal to 0 and y is equal to x dx. So we can plug in our bounds here, and we'll get 0 to 1, and we plug in. Well, y equals 0 is not going to give us anything, but if we plug in x, it cancels with this denominator, and all we get is sine of x dx. Okay, that's pretty easy. So we can get a negative cosine of x evaluated when x equals 0 and x equals 1. Or we can get minus cosine of 1 plus 1. All right, that's the value of the integral. We did it. We did it as a type 1. Now let's set it up and try to integrate as a type 2. So for a type 2, let's go back up to our drawing here. This is where we're drawing the traces in the other direction. So our traces are going in the horizontal. So they start at the hypotenuse and they go over to x is equal to 1. Right? And then what we're doing is we're going in the y direction, and we look at the whole range of the traces. So the traces start going across at y equals 0, and they keep going all the way until they hit this point here, right? Well, we know x is equal to 1 along this line, and then we also know that this is y is equal to x. So it's pretty easy for us to figure out that the point here is 1, 1. Right, so it looks like our y value goes from 0 to 1. So as a type 2, our region is the set of all points in R2 such that y now goes from 0 to 1, but x goes from the value y on the hypotenuse all the way to 1. So here we go from y to 1. So let's set up our integration now. our double integral. So we're going double integral over the region R of sine of x over x dA is the integral from 0 to 1 and then y to 1 of sine of x over x dx dy. So that's the setup. Okay, so now we have to try to integrate this guy. I have sine of x over x, and I'm integrating this with respect to x. Okay. Here's where we're going to run into a lot of trouble. This is called the sinc function, or sine of x over x, has no elementary function for the antiderivative. So you can look it up all you want. You're going to get some wacko stuff. There's going to be special functions, or what you could do is write this as a power series and then integrate, and then integrate with respect to y after that, and then see if you can line it up. But the funny part about this, even though this innermost integral doesn't have an elementary function for an antiderivative, that doesn't mean that the integral doesn't exist. It's just there's really no good way of writing it down. But in combination, these two integrals are the same thing, right? We just chose a different way of representing it. This is still the double integral over the region R. We got a really nice answer here, and here we couldn't even integrate it. So it really goes to show you that we have to be flexible when we look at these regions. Even though this was a region that was both a type 1 and a type 2, one way of integrating was very simple. The other way would be extremely complex, right? And we would have to spend the rest of class trying to do this integral. Let's not do that. Right? There's no way. We would have to, the only way that I could do this off the top of my head is do it as a power series. And no, we're not going to do that here. So if you ever come to a point where you can't integrate, maybe rethink what kind of region you have. Can I write this as the other type? Can I write this as a type 1 or a type 2? And then move from there. Can I do it in the other order? But I have to be a little bit careful, because notice that the bounds that I wrote for these were very different. This went from 0 to 1 and 0 to x, and this one went from 0 to 1 to y to 1. Right? So it's not just that I switched the ordering of the integrals. The bounds themselves will drastically change dependent on if you consider this a type 1 or a type 2 integral. But my biggest suggestion to you, if you ever get to a point where you've correctly written down the integral, but you can't integrate, maybe it's time to rethink it as the other type, right? Maybe recast the region in such a way that it's a type 1 or a type 2. Okay. So let's do an example. Let's just do another one. So this one is, we're going to find the double integral over the region R. That's 4x plus 2 dA, where R is the region bounded phi, y is equal to x squared, and y is equal to 2x. The first thing I'm going to do is sketch the region. I want to know what I'm dealing with. So I have a region in the xy plane. And I know that y equals x squared is this parabola, right? So it doesn't need to be exact, but I know that it's like parabola like this. And then I have y is equal to 2x is a line. So let's go ahead and draw a line, and it does pass through the origin. And maybe it's going to have a slope too. So it looks something like this. So I know that this is my region R. And this is y is equal to x squared. And I know that this is y is equal to 2x. Okay. So before I even start thinking about if this is a type 1 or a type 2, I'm going to need those intercepts, regardless of what type that I want to cast this as. So I'm going to go ahead and find those intercepts. I certainly know that the origin, they both path through the origin, but I need to find this other point here. So to do so, I'm going to set them equal to one another. And you could either set their y's equal to one another or whatnot, as long as you sub one into the other. But notice that I have y on both left-hand sides. So this is just x squared is equal to 2x. So x squared is equal to 2x. So this tells me two things. Either x is equal to 0, or if I divide through by x and x is not 0, then I have that x is equal to 2. So that's the two different outcomes from this. Well, when x is equal to 0, y is equal to 0. Lo and behold, our assumptions that this went through the origin were correct. But if I plug in x is equal to 2, I get that this is the coordinate 4. So this is 2, 4 right here. Okay. So this is another case where this is actually a type 1 and a type 2. What I could do is I could go and do vertical traces like this, where I have a lower function that's defined by my parabola, and go across like this, and then add up all of those traces. Or I could go traces in the horizontal direction that start on the line and end on the parabola. But notice which way that I do this depends on which one is my lower function and which one is my upper function. In this case, I start on the line and end at the parabola. But the other way, I start on the parabola and end on the line. So now that I have these points, I'm going to just choose one of these ways and see if it works. So I'm going to say that our double integral over the region R of 4x plus 2 dA, and I'm going to do dy dx. So if I do dy dx, that means I'm going in the y direction, and I'm making these traces. So I start at the line, and I go out to the parabola. Oh, no, I'm doing this vice versa. So if I do dy dx, I'm doing these vertical guys. So this is actually like this. Yep. So we're going across the y direction. That's our innermost. So that means we're doing our vertical. And then we go in the x direction and add up all of those traces. So I have to put bounds on this still. So my y integral starts at the parabola and ends at the line. And I need them to be functions of x, so that when I do this x integral, I get rid of them. So now I have to think about what my my x bounds are. So my traces, the domain on the traces go from this point to this point. So this is 0 to 2. If you wanted to, we'll talk about if you wanted to, we'll just set up the integral doing it the other way, but we're actually going to evaluate it doing this way. So this is equal to the integral from 0 to 2. And now notice again that this isn't a function of y, so it's pretty easy to integrate. This is y times, 4x plus 2 evaluated at y is equal to x squared and y is equal to 2x dx. So this is the integral from 0 to 2 of 4x plus 2 times 2x minus x squared dx. So we have to FOIL this out, get this as a polynomial. So this is the integral from 0 to 2. And our highest power is going to be here, which is negative 4x cubed. We'll also have a minus 2x squared, a plus 8x squared, plus a 4x dx. Of course, we can simplify this a little bit. This is just going to be plus 6x squared. So we go ahead and integrate this. This is negative x to the 4th plus 2x cubed plus 2x squared evaluated when x is equal to 0 and x is equal to 2. We can plug those values in and we'll get positive 8. No, wait, that should be, I think that's actually negative. Right, we plug in 2 here, 2 to the 4th. This is also 2 to the 4th. Oh no, it is positive. Yeah, because you plug in 2, these terms actually cancel because this is positive x to the 4th, and this is also, this is negative x to the 4th, and this is like positive x to the 4th. Right, and then this is all that remains. So it's just positive 8. Okay, so let's set up the other direction. We won't actually evaluate because we know that it will come out to the same answer as long as integrating it is nice. But in the other direction, we're still going to have a double integral, and we still have our 4x plus 2. And this time, we're doing the opposite direction. So we said dy dx. This is going to be dx dy. Okay, so let's go look at our little plot here and figure out what our bounds are going to be. So now we're doing horizontal traces. and they start on the line and end on the parabola. But we can't just write 2x and x squared, right? Because if we wrote these in terms of x and we integrated out x and then plugged in functions of x, we didn't get rid of x, right? So these have to be an x equals a function of y bounds, right? So we look at up here, we can rewrite these. This line, instead of saying y is equal to 2x, we can say that x is equal to y over 2. And here, we can say that x is equal to plus or minus the square root of y. So we have to be a little bit careful, right? We don't want to choose the wrong sign here. So if you kind of think about this, if you plugged in 4 for y, you should get the positive 2. So we don't use that negative. This is in fact just the square root of y. Okay, so now going back down, we started on the line, which was y over 2, and we went to the parabola, which is the square root of y. Then our traces, so what's the range on y here? Remember, we're adding up, we're doing this in the y direction. The traces range from 0 up until 4. So we can also set this up as 0 to 4. So we can do that as well. This integral might be a little bit more difficult to deal with because you have this radical in the bound that will get subbed in. But it's still very doable, and you'll still get the same answer. But this way, we only had to deal with polynomials rather than radicals. Okay, so before we take off, so one property that may help or may be helpful is that if I have a double integral over some region D, I can write this as the double integral over some region D1 plus some double integral over the region of D2 dA if D is the sum of those two regions. So imagine maybe in the XY plane, the region D doesn't look like a type 1 or a type 2. A good example of this is actually a circle or an ellipse. This is a, well, I guess this is a type 1 or a type, well, yeah, we can write this as a type 1 or a type 2. Let's do something like maybe, I don't know, just a blob. This is hard. So what we could do is perhaps split this up into two separate regions where one of them is a type 1 and one of them is a type 2. So maybe I split it down the middle here. This is actually a terrible shape because I might have to do more than one split. What if I do This is terrible. This is a terrible shape. I would have to do more than just 2 breakups. Let's just do a circle. So a circle can be a type 1 or a type 2, but to get the point across, what you could do is cut it and then consider one region a type 1 and then the other region a type 2. What about an L-shaped region? Oh, that's perfect. Yeah, an L-shaped region. Thank you. Yeah, so what if I do something like, well, if I do something like this, yeah. So I can't do a, this is actually, I could actually do a type, it doesn't matter. The point is, if you separate the regions, what you could do is a region where this is a rectangle, perhaps, or maybe a type 1 or a type 2. And then this way, this other one, we could do horizontal traces like this. Or this way I could do maybe either. But then we can add up the integrals of those 2 regions and piece them together. So the idea is we can separate or can split up the region D to make subsections of it type 1 or type 2 for us to deal with. Okay, and then one last thing. If I have the double integral over some region D where the integrand is equal to 1, this is the area of D. So to kind of think about this, imagine that we were generating a volume where the surface was defined as Z is equal to 1, right? So maybe we're over some region, maybe it's even just a rectangle, but it all has height that's equal to 1, right? So the volume here is the height times the area of the base. So that 1 doesn't really matter. This is just the area of D. So if you ever have an integrand that's 1, it's just the thing that this is just kind of representing. This is the area of D if you're using double integrals. And later on, you can imagine we'll be using triple integrals and so on. So if you have an integrand of 1, it's just the area, volume, whatever of the region D that is depicted by the dimensionality of D. Okay, so with that, we're going to bring it to a close. We'll start up the next section tomorrow. I will see you all then. Stay safe. We're having recitation tomorrow. And we don't have an exam this week.